be heard in the last row. Good.
So, we face this series of 6 lectures with Eric Maston, who's going to talk about the series topic of behavior.
A little narrower than that. In particular, choice behavior under uncertainty. But I'm going to be continuing the theme that Partha established before the break on the interplay between normative and positive considerations in economic modeling. So I'll be using choice under uncertainty as the particular illustration of that theme. So modern choice theory dates back to the 40s, and in particular to the work of von Neumann and Morgenstern. There were strands of the literature on choice and uncertainty even before von Neumann and Morgenstern. In fact, I'll have something to say later on about Bernoulli's contribution in the 18th century, but the theory really got off the ground in 1944. And as I will be showing you, the approach that von Neumann and Morgenstern took reduced choice under uncertainty to maximization of expected utility. And I'll explain in some detail what I mean by that, but very roughly, a utility function assigns a utility to each possible outcome, and there's a misprint there. That should be outcomes rather than options. When you make a choice, typically the outcome resulting from that choice is uncertain. So if you invest in the stock market, perhaps you'll make £100, perhaps you'll lose your money, perhaps you'll get something in between. You don't know for sure what you're going to get. So an option is actually a lottery. And what von Neumann and Morgenstern argued was that you should choose the option which maximizes your expected utility, which is this expression here. For each possible outcome x, there will be a probability px, and you multiply that by the utility you get from x, and then you average over all possible x. So I'll explain how they came up with this in a few minutes, but that's expected utility maximization. And their justification for maximizing this expression was axiomatic. That is, rather than just assuming that a decision maker will be maximizing this expression, they showed that if a decision maker satisfies some more basic and more compelling assumptions, by more compelling I mean not so arbitrary as simply maximizing expected utility, then it will turn out that the decision maker must be acting as though he or she is maximizing this expression. So the approach was axiomatic. And one virtue of the axiomatic method, and after von Neumann and Morgenstern, many other economists followed this approach was that you can understand what's going on better because maximizing expected utility, for example, is a fairly complicated concept. If you can break it down into simpler, less arbitrary assumptions, you may argue about the individual assumptions, and people do, but at least you can understand them. Whereas maximizing expected utility is already complicated enough so that it's difficult to grasp as a whole. Now, on the theme of normative and positive, it's fair to say that the von Neumann-Morgenstern approach is both. It's both normative and positive. It started normatively. That is, von Neumann and Morgenstern weren't arguing that this is how actual people behave. They were saying, if you are a rational decision maker and you are facing conditions of uncertainty, this is how you should behave. But in time, the theory proved to have positive content as well. That is, it turned out to be a pretty good way of understanding a great deal of investment behavior and a pretty good way of understanding insurance markets. And in time, it became the dominant positive theory in the economics of uncertainty. Now, you might find this curious because we know that in reality, not all people are rational. In fact, probably nobody is entirely rational. And even quite rational people make mistakes, whereas the von Neumann and Morgenstern theory doesn't allow for mistakes. But that's okay as long as mistakes are random. That is, even if some people make a lot of mistakes and all people make a few mistakes, as long as there's no systematic direction in which they make these mistakes, then you can argue and correctly that these mistakes will wash out when looking at large numbers. And so as a description of market behavior, where there are lots of people participating in these markets, we can use a theory like von Neumann and Morgenstern despite irrationalities. The problem is that eventually some important anomalies were discovered. By an anomaly, I mean a situation where the mistakes do not wash out, where most of them are in one particular direction, and therefore, even with aggregation, they will not disappear. And it was the discovery of these anomalies which led to a branch of economics which is very popular these days, behavioral economics. And what I'd like to do today is to discuss some of the anomalies that led up to the development of behavioral economics, in particular the paradoxes or the anomalies discovered by Allais, Ellsberg, and Kahneman and Tversky. But before I do that, let me show you the von Neumann and Morgenstern model. And let me also repeat something I've said in previous weeks, which is please speak up immediately if you don't follow something I say, because I don't want to lose you along the way. So, the von Neumann-Morgenstern model. We start with a set of possible outcomes, and for today, although von Neumann and Morgenstern didn't require this, we should think of these as monetary outcomes. So you get a net increase of 17 pounds, or you lose 8 pounds, something like that. And I'm going to stick to the case where there's a finite number of possibilities, but I'll have something to say a little bit later about what happens if there's an infinity of possibilities. So an option for a decision maker is what's in the theory we call a lottery. So as I said before, when you choose an option, you're not guaranteed a particular outcome. Rather, you're choosing a probability distribution over outcomes. So a lottery, which I'll denote by L, is simply an assignment of probabilities to each of these outcomes. So Pi is the probability of outcome Xi. And what a decision maker does is out of the set of available lotteries to choose one of them. And presumably the decision maker has preferences over these lotteries. Here's the notation I'll use. This notation means that the decision maker weakly prefers L to L prime. By weakly prefers, I mean perhaps the decision maker likes L better than L prime, but perhaps the decision maker is indifferent between the two.
What? Could not hear what you said, sorry. Perhaps?
Perhaps the decision maker is indifferent between L and L prime. That is, they might be equally as good. So L is at least as good from the decision maker's point of view as L prime. That's what this notation says. This is the notation for strict preference. So now the decision maker finds L strictly better than L prime. And this is the notation for indifference. From the decision maker's point of view, L and L prime are equivalent. Well, when I said that the von Neumann-Morgenstern approach is axiomatic, I mean that they made certain assumptions about these preferences. In particular, they made 4 assumptions, which I will show you. The first one is in some sense the most standard, and the first part of it simply says that a lottery is at least as good as itself. Now that sounds almost tautological, and it is, but it's there basically for technical reasons. The second assumption is not tautological and has real content. It says that a decision maker can always compare 2 lotteries. So if we take a lottery L and L prime, the decision maker is capable of expressing a preference. L is better than L prime, or L prime is better than L. So completeness or comparability. And then the third part of the assumption is amounts to the assumption that preferences are well behaved. So that says that if the decision maker prefers L to L prime and L prime to L double prime, then the decision maker must prefer L to L double prime. If that were not true, then there would be these preference cycles. The decision maker would go round and round, not being able to make a choice. So that's the first and in some sense the most standard axiom. And on the basis of that, we can go back to the outcomes. Each of these outcomes is in some sense a degenerate lottery. It's a lottery where there's probability 1 of xi. And given our first assumption, the decision maker should now be capable of ranking all the outcomes. Well, there's no harm in assuming that the first outcome is best, the second outcome is second best, and so on. So that's what I will assume, that the decision maker likes outcome x1 best of all, xn worst of all.
Why can't they be indifferent?
They could, but then we could just collapse those two outcomes and make them the same outcome if the decision maker were literally indifferent. The second result is called continuity. And what it says is if we look at the best outcome, which is x1, and the worst outcome, which is xn, and we pick some lottery, L, then it should be possible to find a lottery between x1 and xn such that the decision maker is indifferent between that lottery L and the lottery between x1 and xn. Because after all, if p were very close to 1, then the decision maker would prefer the lottery on the right, because x1 is by assumption the best outcome of all. And if p is very close to 0, then the decision maker would prefer L to the lottery on the right, because xn is by assumption the worst outcome of all. So continuity just says that there's a probability in between 0 and 1 so that the decision maker is exactly indifferent. The third assumption, a pretty weak one I would say, is if we look at lotteries involving the best outcome x1 and the worst outcome xn, and we increase the probability of the good outcome x1, well, that should make the decision maker better off. If we increase the chance of a good outcome, decrease the chance of a bad outcome, that can't be a bad thing. That's called monotonicity. And there's just one more assumption left. Now, this last assumption is slightly more complicated than the others, and it's a good deal more controversial, and a lot of the early work in the anomalies business were essentially attacks on this last assumption, which is called independence. And what it says is this: suppose that a decision maker likes lottery L better than L prime. And now we embed L and L prime into slightly more complicated lotteries, look at the lottery on the left, look at the lottery on the right. The one on the left, the two more complicated lotteries are exactly the same, except that here we have L, and here we have L prime. So this is a lottery where, with probability P, you get lottery L. With probability 1 minus P, you get something else, L hat. This is a lottery where, with probability P, you get L prime, and with probability 1 minus P, you get the something else I was talking about, the same L hat as over here. So notice that these two lotteries are exactly the same, except that here we have L, here we have L prime. Independence says it shouldn't matter what P is, it shouldn't matter what L hat is, as long as the decision maker prefers L to L prime. Whoops. Let me go back to that. As long as the decision maker prefers L to L prime, she'll prefer this lottery to this lottery. This is independent of what, this preference is independent of what P and L hat happen to be. Let me pause for a second to make sure you've digested that, because, as I said, this is the most complicated of the assumptions. There's a sense in which it's a quite natural assumption, I think, given that the only difference between these two lotteries is L and L prime. But are there any questions about it? Well, then let me show you what all of this implies, which is von Neumann and Morgenstern's proposition that if preferences satisfy the four axioms, it must be the case that the decision maker is maximizing expected utility. In other words, there will exist a utility function which assigns a utility to each outcome, so that if the decision maker prefers lottery L to L prime, the expected utility of L, which is this, is greater than or equal to the expected utility of L prime, which is this. So for this expression, we use the probabilities corresponding to lottery L. For this expression, we use the probabilities corresponding to lottery L prime. Yeah.
In a way, when you said that somebody prefers something, it was not defined, right, mathematically. When you said that there was a preference,
Right.
it was not really defined in the whole thing. So in a way, I guess that function should be exactly what you call preference, right?
Well, what von Neumann and Morgenstern are implicitly saying is we start with a ranking of lotteries. So that's the starting point. And we assume that the decision maker has a ranking of lotteries. If that ranking of lotteries satisfies these four axioms, then the ranking of lotteries must correspond to expected utility. There could be other ways of ranking lotteries. One other way of ranking lotteries would be to look at the worst possible outcome and to try to maximize the probability that worst outcome is avoided. That would be a perfectly well-defined ranking, but it would violate this conclusion.
No, this is a proposition, is it? Or is he proven?
This is a proposition, and actually, I will, the proof of the proposition is so amazingly simple that I'm going to show it to you. It's simple and revealing. That is, not only are the steps extremely straightforward, but you can really understand why this proposition must be true when I go through the steps. So that's what I propose to do now, as long as there aren't any more questions about what the proposition actually means. Any other clarifying questions? Okay, so how do we prove this proposition? Well, we're actually going to, given the decision maker's preferences, we're going to construct a utility function that represents those preferences. And so first of all, what we'll do is we'll look at the best possible outcome, which is x1, and we'll assign that utility 1. And we'll look at the worst possible outcome, xn, and we'll assign that utility 0. So all utilities are going to be somewhere between 0 and 1. What do we do for an intermediate outcome xi? Well, we know from the continuity assumption that any intermediate xi must be equivalent, from the decision maker's point of view, to some lottery between the best outcome x1 and the worst outcome xn. That is, there's going to be some probability which makes the decision maker exactly different between this outcome and this lottery. Let's define the probability that creates that indifference to be u of xi. So this is why I say that von Neumann and Morgenstern's proof is so revealing, because we now see that utilities are nothing more than probabilities. They're the probabilities that make you indifferent between a particular outcome xi and a lottery between the best and worst outcomes. And now all we have to do is to show that this assignment of utilities actually leads us to, or leads the decision maker to, maximizing expected utility. And that I can do on a single slide. So here are two lotteries, and P1 through Pn and P1 prime through Pn prime. And let's suppose that the decision maker prefers this lottery to this one. Now, I'm now a little bit worried that is this legible in the back?
Yeah.
So. What I can do is I can reproduce it on the blackboard. So here's the idea. That we start with P1 through Pn, which can be written as a tree like that. And then on the right we have P1 prime, so Pn prime, and what I'm going to do here is to replace xi, in this case it's x2, with a lottery between x1 and xn, where the lottery has a probability u of xi of the good outcome and a probability 1 minus u xi of the bad outcome. And I'll do the same thing over here. And since we started with the decision maker preferring the lottery on the left to the lottery on the right, it must be the case by the independence assumption that the decision maker still prefers the lottery on the left to the lottery on the right. But notice that in this lottery, we've replaced all of the intermediate outcomes, all of the xi's, with either x1 or xn. So this is a lottery which just has x1 and xn. This is a lottery which just has x1 and xn. If we add up all of if we add up all of the probabilities leading to x1, it's the sum of pi u of xi in this lottery. And over here, the probability of x1 is the sum of pi prime u of xi. That's what we have here. But we know from monotonicity that this lottery will be preferred to this lottery provided that the probability of the good outcome, which is this, is at least as big as the probability of the good outcome over here. And that's all there is to the proof. So it may look like magic, maximizing expected utility, but you see from this single slide that it's actually extremely intuitive, because utilities are just probabilities. Basically, you are maximizing the probability of a good outcome. Now, yeah.
I mean, are the utilities ordered? Will the utilities be ordered functions of xi?
Ordered function? I'm not quite sure I
Is u
understand.
of x1 greater than u of x2 greater than u of x3 necessarily?
Yes, the utility of x1 we assign to be 1, and if x2 and the utility of xn is 0, so the utility of x2 will be somewhere between 0 and 1. The utility of x3 will be somewhat lower, and also between 0. That follows from the monotonicity assumption. That's a direct consequence of monotonicity. Now,
Another question just there.
Eric,
yes.
you're given a set of probabilities and lotteries, and you choose today, and then you wake up tomorrow morning and you make another choice. There's nothing to guarantee that your utility function is stable between these two events, is there?
Well, von Neumann and Morgenstern assume that it is, but you're right. That's right. So I think the simplest circumstance to imagine for today's purposes is that all choice is one shot. If it's not one shot, that is, if we make sequences of choices, then we have to worry about such issues as stability and also consistency, whether, even if you have the same preferences, are your choices tomorrow consistent with the ones that you made today?
When you're older and wiser.
When you're older and wiser, you have more information. So, but I'm going to ignore all that. But it turns out that there are plenty of anomalies to worry about, even in a static setting, and I'm going to concentrate on those. But before I do that, I just wanted to say a little bit more about the value of the von Neumann-Morgenstern approach. It turns out that expected utility is extremely easy to work with compared with preferences over lotteries. For example, a very important concept in theory of choice is the idea of risk aversion. Suppose that suppose you face a lottery with a probability p of xi and a probability 1 minus p of xj. And remember, we're thinking of xi and xj as monetary outcomes. Well, the expected outcome, the mean outcome of this lottery is just p xi plus 1 minus p xj. That's the amount you would get on average if you played this lottery over and over again. A decision maker is risk averse if she prefers the expected outcome to the lottery itself. In other words, a risk averter is someone who avoids risk, who avoids probabilities which are strictly between 0 and 1. And risk aversion is such a central concept because for example, it explains why we have insurance markets. If you run the probability, the risk of a big loss, if there's some chance that your house might burn down, might be a small probability, but it's a non-zero probability, then you are probably going to be willing to pay a substantial amount to go from this situation, which is what happens if you're facing the prospect of your house burning down, to this situation, which is what happens when you're insured against that loss. And so people, most people are willing to buy fire insurance because they want to replace the risk with the expected value. Well, why is expected utility so useful in the study of insurance markets? Because it turns out, and you can see this easily, that risk aversion, the desire to go from here to here, corresponds to a utility function which is concave. Because if this is xj and this is xi, then a lottery like this just gives us some points on the line segment which connects xj to xi, point like this, for example. But if the decision maker is risk averse, the decision maker will strictly prefer to replace this point with the utility of the expected value, which is this point. So risk aversion is very easy to describe and to understand in terms of expected utility. It's just concavity of the utility function. Now I said most of the time I'm talking about a finite number of possible outcomes, but if in fact we have an infinity of outcomes, and these monetary outcomes can be arbitrarily large, then it turns out, and this is a point that was noted by Bernoulli, that at least eventually the utility function has to be concave, and let me show you why that is. Here is a famous lottery. It's a lottery called the St. Petersburg paradox. Let's imagine that you are offered a lottery where you have a 1/2 chance of getting £1, a 1/4 chance of getting £2, a 1/8 chance of getting £4, and so on. So you have a 1 over 2 to the n plus 1 chance of getting 2 to the n pounds. So it's a lottery with an infinity of possible outcomes. Now, how much would you be willing to pay to be able to participate in this lottery? Well, let's calculate the expected value, or the mean outcome of this lottery. We multiply 1/2 times 1. We add that to 1/4 times 2, 1 plus 1/8 times 4, and so on. We get an infinite sequence. We get an infinite series where every term in the series is a 1/2. So we get infinity. The lottery has an infinite mean. Now, no decision maker would be willing to pay an infinite amount to play this lottery, and so every decision maker must, at least eventually, be risk averse. That's the observation that was made long before von Neumann and Morgenstern. It was made by Bernoulli, and it was resolved by Bernoulli in 1738.
Yeah. Must in the sense it's a theorem, or must in the sense that it's just a model reality? We should only consider such.
Okay, so very good question. The version of the von Neumann-Morgenstern theorem that I showed you was the version for a finite number of outcomes. There is a version with an infinity of outcomes, and then it is a theorem that utility must be concave in the upper reaches. In fact, you could say more than that. Not only must utility be concave, it must be bounded. Right. That is, utility cannot go to infinity as money goes to infinity.
What do you mean by resolved by Bernoulli?
Actually, Bernoulli's cousin, Nicholas Bernoulli, was the one who first talked about this lottery and was puzzled by the fact that this lottery has an infinite mean. But Nicholas Bernoulli didn't have a resolution to why it is that we're not actually willing to pay an infinite amount to play this lottery. That resolution, or that explanation, was given by Daniel Bernoulli, who said that he didn't talk about utility per se, but in equivalent terms, he said utility must be concave in the upper reaches. That's actually all I plan to say about von Neumann and Morgenstern, and everything from this point on is going to be an attack on von Neumann and Morgenstern, because, as I said, although in practice the theory works quite well, it doesn't always work, and there's some important violations. But before I get to the violations, any further questions?
I
Yes.
just wanted to make a remark about these paradox.
Yes.
In a way, there is a book by Jan Hacking, which is called The Emergence of Probability, and he mentions Pascal's bet, you know, as a first example of decision making,
Yeah.
which is also an example of the St. Petersburg paradox, it seems, because you know you bet with probability. You know, the probability to win is maybe p or 1 minus p. In one case you get 0, in the other case infinity. And I guess you just, it seems to be kind of extreme case
Right.
of your paradox.
Yes, well, it's not clear in Pascal's wager exactly what the expected value is, but I take your point.
0 times infinity.
Right. Good observation. So I want to show you a few famous violations of this model, and the first one was due to the first violation is due to Allay's work, and let me show you the problem that Allais posed. Suppose you're a decision maker and you're offered the choice between two lotteries. One lottery is £1 million for sure, and the other lottery gives you a 10% chance at £5 million, an 89% chance of 1 million, but there's a 1% chance that you'll end up with nothing. Question is, which would you choose? Just out of interest, how many of you would choose the £1 million for sure?
Good chickens.
Vast majority of you. Vast majority of you. Okay, so now I want to look at two different lotteries. Sorry. So you've done what most people do, and they choose 1 million for sure. Now I'm going to show you the other two lotteries. Now we have a choice between a lottery where with an 11% chance you get £1 million, but with 89% chance you get nothing, and a lottery where you have a 10% chance at 5 million, but a 90% chance of nothing. So notice that these lotteries are quite different from the first ones, because chances are you're not going to end up with anything, but you could end up with 1 million or 5 million. Now again, out of interest, how many of you would choose C over D?
I'm going to fall into the trap, so I'm going to choose D.
You can't give the game away.
I would go.
So it looks as though
No, C is the natural one. I'm sorry, D is the natural one.
D is the natural one. I mean, the logic for D is that, look, you're probably not going to get anything anyway, so you might as well get a really super duper payoff rather than just a duper payoff. But,
If the randomization were done by, say, choosing a number between 1 and 100, then I'd have to think a bit more carefully if I was told what the number is. Because if I'm not told what the number is, then I don't really know whether I would have won in the other option. But if I know the number's 11...
Oh, you're being much too analytic about it. I'm asking for your gut feeling. Because after all, most of our choices are from our intuition, not through very specific calculation. Well, in fact, most people do choose D. This has been extremely widely documented in many hundreds, thousands of experiments, both in the field and in the lab. But, and this is Allay's point, if you choose A in the first case, remember A is £1,000,000 for sure, and you choose D in the second case, you are necessarily violating expected utility. And here's why. We can write A, the £1,000,000 for sure, as a lottery where you have an 11% chance of £1,000,000 and an 89% chance of getting £1,000,000. We can write lottery B, which involves the 5 million, the 1 million, and the 0 in this slightly more complicated way. The reason for writing it in this way is that in both this lottery and, in both this lottery and this lottery, there's an 89% chance of getting $1,000,000. So the bottom parts of both these lotteries are the same. But we know from the independence axiom of von Neumann and Morgenstern that it doesn't really matter whether this is £1,000,000 or something else, whatever we put in here, as long as it's the same in both these lotteries, will preserve the preference. So if, for example, we replace the £1,000,000 by 0, then if a decision maker prefers A to B, the decision maker must prefer this lottery to this lottery. But this lottery is C, and this lottery is D. And yet, the decision maker wanted to make the opposite choice, so expected utility is violated. That's the Allais paradox, and it was very influential, and for good reason. Now let me turn to the second paradox. So far I've been talking about these probabilities as though they have some objective reality. And in some cases they do have objective reality. If you go to a casino and you bet on roulette, there are objective probabilities of each of the possible outcomes. But in most cases, in most choices we make in life, the probabilities are not so clear. So if you buy a share of IBM or some other company, the price could rise by $10, or it could go down by $7, or it could stay the same. There are lots of other possibilities. Each of these possibilities is called an event. So going up by $10 is an event. But none of these events have prescribed probabilities. You as a decision maker might assign probabilities, but those probabilities are subjective. They're in your mind, they're not dictated by some objective observer. And so we need a theory which corresponds to subjective probabilities, and that theory was provided by Leonard Savage in the 50s. He took the von Neumann-Morgenstern theorem and redid it for subjective probabilities. And so in particular, I'm not going to go through the details, but in particular, the independence axiom looks like this. If you prefer lottery L to lottery L prime, then you can embed L and L prime into bigger lotteries, just as von Neumann and Morgenstern did, but instead of having probabilities P and 1 minus P, you have event E and the complement of E, that this is not E in these larger lotteries. But otherwise, the axiom is identical. And what Savage showed is that you basically get the same conclusion as von Neumann and Morgenstern if you get rid of objective probabilities, except that now, in addition to asserting that there exists a utility function which corresponds to decision makers' preferences, there also exists a probability function, because remember, probabilities are now subjective. So if you satisfy Savage's axioms, you as a decision maker have a utility function and a probability function, which makes it look as though you are maximizing expected utility given that probability function. So a lovely result, but in practice it's often violated. And the first person to show this in detail was Daniel Ellsberg. Now, those of you who are old enough in this room may remember that Daniel Ellsberg became famous in the 1970s because he was working at the Pentagon at the time, and he was the one who leaked the so-called Pentagon Papers to the press. And so most of the world knows Ellsberg for that, but we decision theorists and probability theorists know Ellsberg for the Ellsberg paradox, which is this. Let's imagine that there's a box. It's a closed box, so you can't see what's inside it, but you're told that inside it are colored balls. There are red balls, there are black balls, there are yellow balls. There are 90 in all. You're told that there are 30 red balls, so you know what the fraction of red balls is. It's a third. But you don't know, you're not told what the composition of the remaining 60 amounts to. They're black and yellow balls. The numbers add up to 60, but it could be that there's one black ball and 59 yellow balls. It could be that there are 59 black balls and one yellow ball, and anything in between. All of those are possibilities. Now, there are 4 possible lotteries. Lottery 1 gives you a payoff of £100 if when we draw one ball out of the box at random, it turns out to be red. Lottery L2 gives you £100 if when we draw a ball at random from the box, it turns out to be black. L3 gives you £100 if either a red ball is drawn or a yellow ball, and L4 gives you a payoff of £100 if it's either black or yellow. Now, Ellsberg was interested in 2 questions. The first is, if you're offered a choice between L1 and L2, which would you choose? In the spirit of experimental economics, how many of you prefer L1 to L2? Remember, L1 gives you a payoff of £100 if we choose a red ball. You know there's a 1/3 chance of that. L2 gives you £100 if we choose a black ball. The probability is somewhere between 0 and 2/3 of that. How many choose L1?
Could be indifferent.
You're not playing fair. Yeah, most people, again, most people prefer L1 to
L1
L2.
to L2.
Now, what about when it's L3 versus L4? How many prefer L4 to L3? Again, okay, this is wonderful. Most people prefer L4 to L3. But you've now violated Savage, because Savage says that you must be acting as though you had subjective probabilities. If you prefer L1 to L2, that means that the probability you're assigning to red is implicitly higher than the probability you're assigning to black. But if you choose L4 over L3, you're saying that the probability of black plus the probability of yellow must be bigger than the probability of red plus the probability of yellow. But now if we cancel the yellows, the probability of yellow, we get the opposite inequalities here. So we have a contradiction. You violated Savage. And that's a big deal. Because it turns out that we often violate Savage in exactly this way. Let me show you one more paradox. Sure.
These Ellsberg's questioning, does it suggest that people aren't used to using the principle of insufficient reason? By saying that since I don't know between the black and white, the yellow, I'll assume it's half.
Yes, that's right. So there's a very old idea, again going back to the 18th century. I think it was Laplace who proposed the principle of insufficient reason, which is that if you don't, if you can't say which event is more likely than the other, assign them equal probabilities. But
in this case, that is true, right? In that case, it is true. Yeah. If you don't know anything else.
Well, if you use the principle of insufficient reason, then you should be indifferent between L1 and L2, and you should be. But actually, people strictly prefer L1 to L2. So how is this behavior explained? I should say that for all these violations, there is an expanded theory which explains the violation, so this violation leads to a theory which suggests that we're ambiguity averse. You see, if we choose L1, there's no ambiguity about what the chance of winning is. It's a third. If we choose L2, it's not so clear what our probability of winning is. Somewhere between 0 and 2/3, but we don't know exactly where. And one way of resolving that would be to say it's exactly a third, but that's not the way that human beings assign probability. We don't like ambiguity just because it's ambiguous. And if we introduce ambiguity, it turns out you can take the Savage axioms, relax them, impose ambiguity averseness, and then reconcile actual behavior with theoretical prediction pretty well. But we have much more trouble reconciling the last paradox with theory, and that's the Kahneman and Tversky framing paradox. So here's how that works. Suppose we have a town consisting of 600 citizens, and suppose that unfortunately they're exposed to a potentially deadly virus. Well, the public health health officials rush in, and they have two different treatments that they could possibly implement. They have to choose between treatment A. Treatment A is going to save 200 lives. So there's not any uncertainty here. We know that these 200 lives will be saved, but we don't necessarily know which lives those are. Treatment B has a more uncertain outcome with a 1/3 chance everybody will be saved, 600 lives, but with 2/3 chance no one is saved. Now let me continue to throw it open to the floor. How many of you prefer treatment A to treatment B? If you were the public health authority, which would you choose? A? How many of you would choose A? Okay, so, all right, so it looks as though it's a weak, it's not an overwhelming majority, but at least a simple majority. And in fact, that's a representative outcome. Again, most people do choose A over B. Now let's look at two other treatments, C and D. In treatment C, we know that 400 people are going to die. In treatment D, we have a 1/3 chance of nobody dying and a 2/3 chance of everybody dying. How many of you choose D? No discussion. How many of you choose D? You're indifferent. Okay. Again, most people do choose D, but observe the following. A is exactly equivalent to C. Because saving 200, remember this is a deadly disease. If we save 200 lives, that's the same as 400 dying. And if we have a lottery between being saved and nobody being saved, that's equivalent to a lottery where nobody dies and everybody dies. So A is equivalent to C, B is equivalent to D, so it's inconsistent for you to prefer A to B, but D to C. In other words, how the problem is framed, how the problem is described matters, even though the talking about saving people and people dying leads to exactly the same outcome. The language itself matters, and that means that we have to be very careful when presenting people with options, or people have to be very careful for themselves when choosing among options to translate that language into outcomes. And people don't always make that translation. In fact, they systematically get that translation wrong. That's what Kahneman and Tversky showed. And so a lot of behavioral economics has come out of this kind of example.
There's a question.
But is there any quantitative reason why people prefer A to B? I mean, the expected value of life saved is the same.
There is a well-developed theory for why people prefer A to B, and it has to do with the idea that if you use the language save, then the idea that in treatment B, there's some chance that no one will be saved becomes the salient feature. So it turns out that in questions of uncertainty, the variable which is salient, you can often say in advance what the variable that's salient will be, will tend to loom much larger than it ought to from the point of view of von Neumann, Morgenstern, and Savage. So even this problem can be theoretically reconciled. In fact, it turns out, so I've shown you 3 anomalies today. It turns out that there are quite a few more. There are 8 or 9 more. Depending on how you count them, there are about a dozen extremely well documented anomalies in choice theory, violations of the von Neumann, Morgenstern, and Savage axioms. Now, that's the empirical side. For each of these violations, we have a model which reconciles the violation with theory. That is, we expand the theory to account for the violation. But that means there are 12 models. And that's quite a proliferation from the old days when there was just one model, the von Neumann-Morgenstern model. The big theoretical challenge lying ahead for behavioral economics, if behavioral economics is really going to leave a lasting imprint on modern economics, there's going to have to be some unification of these models. We don't have that unification yet, but to the economists in the audience, this is the big theory challenge, I think, for the future, to unify them all. And with that challenge, let me stop. Thank you very much.
Is there any last questions before we close the meeting? Yes.
Well, an obvious question. If you know people are systematically biased, and you know how they're systematically biased, but you have to take a decision for them, what approach do you recommend?
Well, so there's been quite a lot written about that. In fact, there was a popular book that was published a few years ago by Sunstein and Thaler called Nudge. The idea is that if you know people are going to make the wrong decision a lot of the time, and you don't want to take over all of your decision making, or you don't want to take away all their decision making. You want to still give them the freedom to choose, but you're worried that they're going to make the right choice. Then you can cast the problem in such a way that they're more likely to do the right thing. So here is another well-documented anomaly, which Sunstein and Thaler made quite a lot of. If you offer people retirement plans, in the U.S., it's typically employers who are the primary provider of retirement plans. If you offer them retirement plans, then even though an employee would be better off by taking any of the retirement plans and arbitrarily than no plan at all, employees typically postpone making the choice. So you offer them 3 retirement plans. Any of them would work, but they don't want to think about it, so they don't choose any retirement plan at all for years. What Sunstein and Thaler say is what employers should do is to change the default. So you're automatically enrolled in some retirement plan unless you choose to disenroll yourself. So you're allowed to do that. And now, actually, many employers are following exactly this strategy. If you change the default, you don't diminish people's freedom of choice, but you get a better social outcome. The same thing with organ donation. In the U.S., if you don't specifically check a box when you apply for a driver's license that should you be killed on the highway, all of your organs will be donated to deserving people, then the organs are wasted. You have to make a deliberate choice that you will donate. But most people don't bother to do that. If you ask them, are you in favor of organ donation, they will say yes, but they don't make the election because it's too much trouble to read the form completely. In other countries where organ donation is the default outcome, you get much higher rates of organ donation. So that's the sort of thing that an informed or benevolent authority can do on behalf of people without taking away their ability to make choices for themselves.
So in both cases, you're essentially saying these are normative choices that the decision, well, the person acting in this case, is making on behalf of other people.
Yes, that's right.
Even though they may pretend that it is revealed preference, and to that extent.
Well, they don't. They don't even. At least in the U.S., it's not. There's no pretense even made. That is, the people, employers, for example, who have followed Sunstein and Thaler have done it quite openly. But there's been and there has been resistance by people who think that even this rather benign meddling is still meddling, but on the whole, it's worked pretty well so far. These suggestions were made just a few years ago, so it's too early to tell how it's all going to turn out.
The St. Petersburg paradox depends on the existence of outcomes with arbitrarily large utility. Now,
Yes.
even Pascal didn't claim that. He claimed there's one outcome with infinite utility, but he would I think have conceded that there's an upper bound to the utility of all other outcomes.
I would wager that Pascal would have given that answer if he were pressed. Did he ever discuss arbitrarily large outcomes in his writing? I'm not aware of
think so,
that.
but the implication in his writings is that there aren't any.
So there's just this one particular outcome
Just
which
this
happens to
one
have
particular
infinite
outcome, which is
yeah.
paradise.
Right. Okay. So perhaps Pascal anticipated Bernoulli by 100 years or so.
Yeah.
That's
There's a gentleman here have one question.
I have the impression, please correct me if I'm wrong, that the classical paradigm of expected utility maximization works somehow with the assumption that human decisions are based on a certain mechanical framework. You have certain inputs, the brain computes something, and you have an output. And now we have all these anomalies and see that this framework doesn't always hold. And you told us that it's quite hard to find a new framework that still works in a comparable way. so that you can compute decisions by knowing the inputs and then knowing the outputs in a systematic way. And how far do you think this is really necessary or a worthwhile undertaking, or could we also work on the basis of a just positive empirical framework where we observe what people do but do not necessarily know if there's some mechanic process going on, or if they just behave on whatever basis their decisions are based on, but just by establishing certain correlations, like maybe Google does when establishing what I might be interested in without having a theory about my mind?
Well, very good question. There are two parts to the answer. The first is that von Neumann, Morgenstern, and Savage and the rest are not theories about the mind. They're not asserting anything about what is actually going on in the mind. They're saying, though, that choices, empirical or theoretical choices, can be explained by a particular maximization of expected utility. But they're not asserting that the people who are making these choices are doing any calculation whatsoever. Now, you might ask, well, why do we need a theoretical prediction of what they're going to do? And that comes back to things that David was asking about, and Partha was talking about. If you change the parameters of the problem, suppose that through policy, you could create additional lotteries that people might choose from. Corresponds a bit to raising the parameter A in the sort of exercise that Partha was talking about. You want to know before you actually do that what the likely outcome is, but for that you need a model. You need a theoretical prediction, and that, I think, is why it's so important to be able to have a framework which accommodates the anomalies but still makes accurate predictions before the parameters have actually been changed.
Maybe one last question before we
Okay. Okay, well, all right, if it's going to be the last question, I'll ask you this. Sort of coming from people, say, in cognitive science, artificial intelligence, they might say that economists are focusing all their attention on the wrong problem. Yeah, you're asking how to make rational choice. The really challenging problem is a classification one. How do I know when I'm when it's time to make a decision and what the options are?
Right. Well, actually, David Newbury over there was asking something similar when he said, "Well, what if tomorrow my preferences aren't the same as today? How do we reconcile what I do today with what will I regret my choices tomorrow if I decide today? Maybe I'm better off waiting till tomorrow before making any choices at all." So that you're asking about the timing of decision. How long do we wait before we make a decision?
How do I know that this is a situation in which I should make a decision?
Well, that's right. That's also a decision-making under uncertainty problem. You don't want to make a decision too early because you may not have enough information to do the right thing. You don't want to wait too long to make that decision because in the meantime, not acting can be harmful. We were talking about retirement plans a few minutes ago. These employees were offered retirement plans. They didn't want to think about it. So just comparing them was costly. They decided to postpone that cost to the future, but in the meantime, they were failing to save for their retirement. So you're asking, well,
So I'm asking sort of the ontological question here. How do I know that there is?
well, you don't know. So you never know exactly when you should choose. That's a lottery as well. And an economist who's doing his job ought to be able to say something about the timing of decisions as well as the content of decisions. But it's a hard problem. I'm pretending we have an answer to that to that question yet. But that's part of what behavioral economics is moving toward. It trying to get to discern the empirical regularities in the hope that a theory, or at least a manageable number of theories, will come along to let us make predictions like that.
Just thinking that at the moment some people probably haven't read the schedule or heard warning of this, and so at the moment they don't know that out there are going to be some drinks for us, and so at this moment they don't have a preference.
I think you just suggested that there's a very strong preference for adjourning and having a drink and continuing the discussion informally. Thanks.
I was just about to say that the drinks reception at the end does present a nice opportunity to continue some of these very interesting discussions. So please do join us just outside there for some wine and conversations. And I'd just like to thank, on behalf of the Isaac Newton Institute, Professor Gupta and Gus Gupta and Professor Matthew, for giving us a very valuable time to come and give this series of really interesting talks. So thank you both very much.
Thanks all.